So there will be in the first week of June 6th to June 8th, there will be a conference here. So one thing you need to know that there will be no class on the 8th, and you're all invited. And continuing your question, there will be two talks about deep networks and one about more application, and the other would be more about more conceptual talk. These talks will be on the 7th, I think. But the conference is... Okay? 3 days. No, this is a Gatsby Tri-Center meeting. It will take place here, yes. There will be an official announcement next week. It's a meeting about computational neuroscience, basically. Okay. So Itamar told you all that you need to know about the effect of beta, about temperature, or the effect of the shape of the input-output function of a single neuron on the ability of the network to maintain memory patterns. Today we will go back to the zero temperature binary neurons case, and I would like to start with an exercise, a small exercise. So we computed the capacity of the network in the Hopfield model, where we had patterns that were plus and minus 1 with probability 1/2. And we used the Jij is equal to 1 over n, sum over mu, pi mu, pj mu, and we had Si is equal to sine hi, large N. I think this is pretty much it. And we use this model and we computed the capacity of the network by looking at the number of the probability that a memory pattern will be a fixed point of the dynamics. The dynamics is being Si dot is equal to minus Si plus this would be sine of hi. This is the case of the limit of beta going to infinity. Questions? So, as an exercise, I would like to start by considering this model, but making the memory patterns sparse. What do I mean by sparse? Choosing plus and minus 1, not with a probability of 1/2, but with a different probability. So the probability that pi mu is equal to 1 will be equal to S. Questions? Any questions?
Not sure.
Not sure that you have a question?
Yes. Not sure that it's good enough.
You're not sure you have a question, but you're not sure that you want to share it.
Yeah.
Okay.
Thank you.
Yes. Well, that as you remember, Jennifer Aniston will evoke will evoke activity only in a small subset of neurons. Not half of your neurons in the brain will be active when you're presented with Jennifer Aniston.
So that means that the memory pattern is smaller than the network, or?
No, that most neurons, for example, will be inactive. in each memory pattern.
F is smaller than half.
Yeah. We can think about the general case, but let's say that f is smaller than half, maybe even much smaller than half, maybe 1%. What would be the capacity of this network to store memories?
Does it mean that everything that's not 1 will be -1?
Yeah.
This is an act?
Yes.
-1 can't be part of a memory pattern?
Well, I mean, there is information about the fact that neurons are not active, right? But it's also if you look from the outside, you present a stimulus to the brain, to the animal, and you look at activity and you see that some neurons do not respond. This is also informative about the stimulus, given the fact that these neurons will respond to other stimuli. But bear with me, we will consider the case of f being different from 1/2, thinking about the case of sparse memories. There are other variants of the Hopfield model in which SI can be either 1 or 0, and then the idea of sparseness perhaps makes more sense. The probability that the memory pattern will be 1 is f, and the probability that the memory pattern is 0 will be 1 minus f, and then the connectivity matrix is slightly different. But let's consider the good old connectivity matrix with this assumption that the probability of a pattern being 1 or -1 is not half, but different from half. Yes.
JII still equal to 0?
Yeah. Whatever. Yeah. Okay. So the question is, what would be the memory capacity? So how are we going to solve it? Well, one naive way is using the same approach as before and asking the question, what is the probability that a memory pattern will be a fixed point of the dynamics, going one neuron at a time, as we did previously. Right?
Right.
Good. So let's do it. Thank you. So how are we going to do it? Yes?
Can I take the go?
Yes? Yes. This was not a rhetorical question. It was a real question. How are we going to do it?
We need to find a condition for which the memory pattern will be a fixed point.
Right.
Then we can do like a mumbo jumbo algebraic acrobatics.
Okay.
And then we get a feeling about how it's distributed.
Okay, so let's do it.
Okay, so let's start with taking x close to 0 and choosing yes. Yes.
Yeah, okay.
And plugging pi nu instead of si.
Okay, so we're interested in HI, or more precisely, we're interested in the question of whether the sign of SI is equal to the sign of HI, given that all neurons in the N2 network are in a particular memory pattern, let's say the first memory pattern. So basically, we're interested in the sign of this term, pi1 times h, which would be equal to sum over j, jij, pj1. This is what we're interested in, as before. If it's equal to 1, well, if it's positive, then we're happy. If it's negative, well, then we are unhappy. Right? That would be... but maybe we can just look at this term. And eventually we will ask whether it corresponds to the first one or does not correspond to the sign of this term, whether it corresponds to the sign of pi1 or not. Okay. So what was... This was... acrobatics, what was the term that you were using? Okay, so how are we going? Yeah, what's the next step? Okay, so this is equal to 1 over n, sum over j, sum over mu, pi mu, pj mu, and just for you, I'm going to write here j is not equal to I, okay? Times pj1, right? Okay, next.
Open the sum. So the first term, the other.
So we take the sum over mu, sum over all memory patterns. We divide it into the first memory pattern and all other memory patterns, right? That's the next step. Okay? Okay. So we take the first one, which is a pi1 pj1 times pj1. And here we are very happy because we have pj1 squared. So it's a reason for celebration. We have kind of plus sum over mu, pi mu, pj mu, mu is larger than 1, pj1. And here allow me to take just to do the next step. So this will be equal to pi1 up to these things that we don't care about, 1 over n, right? Plus 1 over n, sum over mu larger than 1, sum over j not being equal to I, pi mu, pj mu, pj1. Right? As before. So at least we're making progress because at least the first term is what we want. Not surprising because we've already done it. Okay, now we have a second term. What do we need to do with the second term? Yes. Yes. It's asymptotically we're taking the limit of very large n, so this would be asymptotically pi1. If you want, you can.
Distribution.
Okay, so this would be equal to pi1 plus, as before, sum over k. I think we called it zk, and we had n. Should I say n minus 1 times p minus 1 or
NP.
or np?
N minus 1.
No. Well, I'm going to.
If you are
It's asymptotically equal to. Okay, I will leave it as before. Okay. Fine.
Make sure, what is the assumption right now about P?
No assumptions.
Okay.
There are no assumptions.
You don't assume that it's allowed?
Well, of course, we'll be interested in large P, but writing it this way, there are no assumptions about P. So, and I forgot the 1 over n. How could I do that? Okay. So what is zk? What possible values can zk have? Either plus 1 or minus 1. Okay, what's the next step? Well, if n is large, even if p is not large, this would be this term 1 over n sum over k. Zk will be normally distributed with some mean and variance. And our next step will be what? To compute the mean and variance. Okay, let's start with the mean. So the mean of 1 over n sum over k zk will be equal to 1 over n sum over k of zk, which is also equal to 1 over n times n minus 1 p minus 1 average of zk. Right? And what's the average of zk? As before,
No.
it's It's not as before. Thank you. What's the average of ZK?
We need to
F,
take
something with
no,
F.
no, 1
No,
times
not
F
F.
minus 1 times 1 minus F.
Well, okay. So previously, ZK was plus and minus 1 with probability 1/2. Now this is no longer true. So let's see. So ZK will be equal to 1. What's the probability that it's equal to 1? Well, ZK is a product of 3 numbers. Right? ZK is a product of 3 numbers. This one, you can do it here. This one, and this one. It will be equal to 1 if all of them are equal to 1. That's one possibility. Or 2 out of the 3 are equal to -1 and 1 is equal to 1. So what's the probability? What is the probability that all 3 will be equal to 1? F cubed. F plus
2 choose 3
plus
yes, thank you. Like the binomial times
which is equal to?
3.
What's the probability? Well, thinking about it, it's the minus. We have 2 plus 1s and 2 minus 1s and 1 plus 1. The plus 1 can be either here, or here, or here. So that's 3.
3f times 1 minus 12.
Thank you. Is it clear to everyone why this is the case? You okay? Or it will be equal to -1 with probability. What's the probability of a -1? 1 minus f cubed plus 3 f squared 1 minus f. It's kind of ugly, right? Because you have all these numbers. So we'll just for the sake of just for the fun of it, we will take the limit of small f. We're interested in sparse networks. So what will be the dominant term here? This would be 3f, and this would be 3f squared. I heard 3f squared. Why can't this be? Well, there are 2 trivial ways of seeing it. Well, it has to be 1 minus 3f because it's a complementary. This plus this has to be equal to 1. Or alternatively, we can just open this and we have 1 minus 3f and the rest are order f squared. Okay. So ZK is equal to the average of ZK, 3f times 1 plus 1 minus 3f times -1. Which is equal to 6f minus 1. So what are the implications? So the implications are that this term, 1 over n sum over k, zk, is normally distributed with a mean of n minus 1 over n, which is 1, basically, times p minus 1, times 6f minus 1, and we still have to compute the variance, right? right? No. We don't have to compute the variance. Why don't we have to compute the variance? What do you mean by big? Is 7
more
big?
big than PI1.
Well, okay, so it depends. So n minus 1 over n, you all agree that it's exactly 1, mathematically exactly 1, okay? Let's say that f is small, which we assume that it's small. Maybe it's 1%. So this is minus 1. And let's say that p is 3. If p is 3, well, this would be approximately equal to minus 2. Not good. No, because this is plus or minus 1. But who cares about this term if this is normally distributed around minus 2? So what are the implications?
And the variance, like, would be the highest in the when the probability to get 1 or minus 1 is the same, right? So anyway, it's going to be smaller than over n.
Well, there are two possibilities, okay? One is that the variance is going to be large, or that the variance is going to be small. Of course, there is also an intermediate. Wait. I'm answering your question. I'm serious. And also, of course, there is an intermediate range. But let's consider these two possibilities seriously. If the variance is small, it will turn out that the variance is small. Then, basically, we don't care about the variance. It's like always adding minus something. If, for example, if p is equal to minus 3, always adding minus 2 to this h term, which implies that all neurons will immediately become minus 1. So we don't. So the memory pattern is not a fixed point. That's the first possibility, which will turn out to be true. Wait, bear with me. You will have. You will be able. I will let you stand here and take the rest of the class. Second possibility is that the variance is large. Let's say that the variance is large. If the variance is large enough, larger than this minus 2, well, this will imply that the outcome, the sign of h will be plus or minus 1 with the probability 1/2, and also we will not be able. The memory pattern will not be a fixed point. So in that sense, we don't care about the variance because independently of whether it's going to be small or large, we have a serious problem here. We are unable to the capacity of this network to maintain memories is basically 1 or 2, unlike the n that we discussed last week, or even n over log n.
Unless 6f is 1.
Well, if 6f is 1, then f is
not half. One of the three.
Okay. So if f is small, then this is a horrible model for memory. Okay. Now, if f is equal to 1 over 6, well, this seems to be a good idea. This would work, right?
Yeah.
So this is kind of weird, right? It works for f being equal to 1/2, right? This is what we did here. And it works for f being equal, just a second, it works for f being equal to 1 over 6. What about all the intermediate values? Approximation. Okay, so you're absolutely right. It's all because of this. Okay, if f is relatively large, then this approximation doesn't hold, and it will turn out that this will work well if f it will be equal to 1/2. But okay, so we had this fun exercise. Oh my God, it took us half an hour. זמן טס כשנהנים. we had this exercise, and we learned that this model doesn't work well if f is small. And in fact, if you follow this argumentation, it will not work for any f that is not equal to 1/2, which is a serious concern if we think about the Hopfield model as a model for associative memory, right? If we think about Jennifer Aniston and the fact that she activates only maybe 1% of the neurons in a particular brain region, well, we will not be able to remember her, or at least we will not be able to remember anything but her, because still we have a memory capacity of one pattern. So this of course will not work, and this is a serious issue with the Hopfield model. It turns out that the Hopfield model, this issue that the probability is half is a strong requirement. One way of thinking about it is the fact that maybe I will make this point in two more sentences. First, I'll answer the question.
Yeah,
Yes.
but what if you have a lot of networks in your brain, that each one works independently, and then this network is for all sorts of memory, and then only this memory will have half of their neurons lit up, but it's not much.
So so the idea is that each memory pattern will be represented by a different network. It's a good question. I will answer in a second. Yes.
What is we need only the mean need to be 0, and the VI can be more and less than 1.
So the different memory patterns each will have a different probability. That's such that average over all patterns you'll get 0. So that's also a good question. So I'll start by answering your question. So basically we understand that we have an issue here, that this term has to be 0. And one way of making this term 0 is by choosing. So what are the possibilities? One will be to choose the memory patterns to be +1 and -1 with a probability 1/2. This would be one possibility. A second possibility would be to say, okay, and that's your suggestion, let's assume that different memories have activate a different fraction of neurons, such that average over memories will get 1/2. For example, Jennifer Aniston is only 1% of the neurons in your memory area, but I am 99%. I activate 99% of these neurons, such that on average you'll get this 0. Well, that's an interesting idea, but it turns out that it will not work well because it will make the noise substantially larger. I mean, it's better than this case, but the noise will be substantial. Will be large. Will be larger, and so this would be an issue. I mean, one way of understanding it is, let's say that all you have in your brain is me, Jennifer Aniston, and two more good friends with some, I don't know, 0.7, 0.3. Now, you didn't know me a few months ago, right? So I was not one of these memories. So before you knew me, you only had your two friends and Jennifer Aniston, then you were already in this regime where it didn't work. Okay? So you needed me in order to be able to remember your friends. It doesn't make much sense. But mathematically, these would be the implications. Another possibility would be to change the learning rule. And one learning rule that people often discuss, it's known as the covariance rule. Covariance rule. And in that case, j is equal to 1 over n, sum over mu, pi mu minus average pi mu, times pj mu minus average pj mu. And you can immediately see that for the case in which pi mu is plus and minus 1 with a probability 1/2, we get the original Hopfield model. And if we use this model, then we will have a term that will be subtracted here, and this I will leave it to you as an exercise. This would result in this term being equal to 0. So that's one solution. But we have a problem here, and the problem is that this solution requires some form of fine-tuning in the brain. Previously, the fine-tuning was hidden. When writing it this way, what was hidden was the fact that we have a mean subtraction. So if we have a mean subtraction like this, the model will work very well. If we subtract not the mean, but 0.95 of the mean, the capacity will become order 1. This will have catastrophic consequences for the ability of the memory to maintain memory. So the idea of mean subtraction, I saw that I will answer in a second. The idea of mean subtraction is something that we encounter in biology all the time. It's called also adaptation. But the thing is that in order for this model to work, we need the adaptation to be perfect. In order to in order to construct a model that will be able to maintain a large number of memory patterns, order n memory patterns, we need the mean subtraction to be perfect. Otherwise, we will end up with an order 1 capacity, even in very large networks. You had a question. You have a question. I still owe you. I still owe you an answer. Yes.
Two things. And the first one, actually, a notion. I think you talked about it in a different course, but it's as if we expect a single neuron to know the expectance of the entire network, which is.
No. The neuron can subtract. I mean, if you have a large number of memory patterns, the neuron can subtract its own activity, its own average activity over all these memory patterns. But it has to do it exactly. Not approximately, but exactly.
The mean here is on mu?
Well, the mean here is on the realization of memory patterns, which is on everything we can, the realization of memory patterns. Second question.
Maybe I missed something, but why do we have to have an expectation distribution of 0?
Well,
It was like this.
So let's go back to this term. So basically, we will have the mean will be a large number, n times p, times the average of zk. If the average of zk is not 0, then this would grow very fast. Well, we have 1 over n here, but 1 over n will cancel out with this n minus 1. So basically, we have p times the average, this average. Now, once p times this average is larger than 1, or smaller than minus 1, then we're done.
So is this 0 true only for this model of the sparse? This notion about the zero expectance is true only about this sparse memory?
Well, this is for any f that is not equal to 1/2.
Okay.
When f is equal to 1/2, basically writing the model like this is assuming a perfect tuning of the model to the distribution of memory patterns. You had a question.
Why here the capacity would be 1, order 1?
Well, once this is equal to -2, let's say, or minus 1.1, then the input to the neuron will be always negative independently of the value of pi1. So all neurons in the network will become -1.
I'm talking about the learning group.
So you're asking how this is going to solve it?
No, I'm asking, maybe I misunderstood. I thought you said that if it's not exactly the mean that you subtract, then the capacity will be over the 1.
Yes, because if you don't exactly subtract the mean, then this will be no longer equal to 0. I'm not proving it to you, but you can. This is something that you can do on your own. It's not.
So you're saying there will be a bias towards 1.
Yeah, there will be a bias of the entire network towards being all 1 or all -1. Okay, now I'm going back to your question. So you're saying, okay, I have a new model of memory, which basically says that the memory is not distributed across all synapses in the network, but we have sub networks, each corresponding to a different memory pattern, and they're not in some sense are not correlated or not very correlated. And it could very well be that this is what's going on in biology, but I'd like to highlight the shortcomings of your suggestion. Okay, and this would the idea would be to think about it from information theory perspective. So the memory capacity. How many? So let's take it to the extreme, maybe. Okay, let's say that each neuron, each pair of neurons. Okay, a pair of neurons in the network is a memory pattern.
You need n larger than 1, right?
Two. Two is larger than 1. I mean, we had this issue with what was it? 6f minus 1, but still 2 is larger than 1, or maybe 3. Okay, let's say that we're considering networks of 3 neurons, or maybe 4. Okay, 4. Last number, 4.
You won't be able to store much memory.
So each one will store a single memory pattern. So the good thing is that you're still in an order n number of memory patterns. So it will be n over 4. You have n over 4 networks, each one being able to store one memory. But how much information is there in this memory? A memory pattern of 4 neurons has only 4 bits of information. So you have n over 4 memory patterns that you can store, each one 4 bits. So basically, you store n bits in your network. In the original Hopfield model, you're able to store something like n memory patterns, each one with n bits. So you have n squared bits. So your solution, while a possibility in the biology, has its limitations. The ability to store information is substantially smaller. Okay? More questions? Okay, so this was an example, and I leave it to you to show that this is a solution. What I want to do now is to think about capacity in a completely, well, not completely, but in a different framework. And if we talk about the history of neuroscience, these models are models from the 1980s. The story that I'm going to tell you is something more recent. This is based on a paper by Stefano Fusi and Larry Abbott. That was published in 2007. It's a Nature Neuroscience paper. And actually, it is based on all the work that Stefano Fusi did as I think as a graduate student with the late Daniel Amit in the late 90s. And the one question that concerned them was the following. So in this model, in the Hopfield model, in the original Hopfield model, how many values can a synapse obtain? How many different values can a synapse obtain? How many different efficacies can a synapse have?
Depends on n. Depends on mu, I want how much too.
It depends on P, more precisely.
Yeah, P is how much
So in principle, the number of different synaptic efficacies that the network can maintain will be, in principle, it's infinite. And if we have P memory patterns, the maximal the maximal efficacy will be P over n. The minimal efficacy would be minus P over n. and and you have all the steps on the way, p plus 1 different
I
values.
think the question you asked wasn't so clear. I didn't understand.
Okay.
What do you mean by efficacy?
Well, these are synapses, okay? They have weights. JJ, what is JJ?
Okay.
JJ is the synaptic efficacy, strength of a synapse. Now, according to this model, a synapse can maintain different values. It can maintain a value of minus p over n, can maintain a value of plus p over n, can maintain a value of 0, can maintain a value of 1 over n. There are many, many different values that the synapse can maintain. Now, if n is large and p is large, then the number of different values that the synapse can maintain is large, is very large, will be on the order of p. And
you mean to patterns.
Yeah, number of patterns. But number of patterns, if we think about the capacity of network, is on the order of the number of neurons. So if we think about, I don't know, 10 to the 6 or 10 to the 7 neurons, then at least according to this model, the number of different values that a synapse can maintain is on the order of, 10 to the 6, 10 to the 7 different values. Yes?
Maybe it's not so related to this discussion, but what do you mean by maintain?
Well, think about a synapse as it's a biophysical device. So let's say that you measure the number of receptors in the postsynaptic density is a measure of the strength of the synapse. So maybe you can have, 20 receptors, maybe you can have 25 receptors, and 25 will be stronger than 10. But if you think about receptors in the postsynaptic density as a measure, now you have a biological limitation on the discreteness, on the number of different efficacies that the synapse can maintain. You don't have 10 to the 7 receptors. You have a smaller number of receptors. This is one problem. Another problem is that a synapse is a biological entity, and there is noise. So there is some. If we think about a synapse as a biological entity, it would make sense to think that the number of different values that it can attain is smaller than order n. Maybe, I don't know, maybe it can attain 50 different values, maybe 100 different values, maybe 10. And what Daniela Mead and Stefano Fuzzi asked, and later Stefano Fuzzi and Larry Abbott, was what are the implications of limiting the number of different states that a synapse can attain? This was the question that they asked. What would be the implications regarding the memory capacity of the network? Now, this is a difficult, in principle, this is a difficult question to answer, because it could be, for example, that for this learning rule, it will not work well, but if we make this change to the learning rule, it will work well. So they wanted to ask this question in a more general framework, saying something like, let's consider a large family of learning rules and try and come up with an answer to this question of capacity while limiting the number of states synapse can maintain.
But it seems to be less biological driven.
What?
I mean, I would guess that the values that synapses can have is very, I mean,
Well, what?
it depends on many, many parameters.
Right.
And I don't think it's like a set of values that you can get, and it's like, it depends on.
Okay, that's a good question. So what you're saying is you're challenging the underlying hypothesis of the model. So the answer would be, okay, fine. I mean, we can see the results and then go back to your comment. That's one thing. And second thing that they would tell you is it's not necessarily true that a synapse is a discrete entity. In fact, if we look at the literature in neuroscience, this is a question of a lot of controversy in recent years. Some people think that potentiation and depression are binary events in individual synapses. There is a claim. Peterson, Sam Wang are proponents of this idea. Other people, a synapse can be in one of two states, either potentiated or not potentiated. These are the two states, only two states. This is a claim, and the fact that we see graded results from averaging and noise. That's a claim that appears in the literature. I don't believe it for other reasons, but it's a respectable claim. This is one possibility. In that case, the whole idea of Gij being able to attain order n number of states doesn't make any sense. This is one claim. Another claim would be the following: it is true that synapses are analog entities, but it doesn't make sense that they can maintain all these values in view of the noise in the system. So the idea would be that you have a synapse can attain almost any value or in a range of values, but there's noise, like random walk or kind of noise that results in inability to maintain all these values. Sometimes you just drift a little bit weak potentiation or weak depression. So you have noise, and the effect of this noise is that effectively the number of states is relatively small.
Noise has an effect?
Biological noise. Because the idea is that a synapse is I trained the synapse to be with some number of patterns, and now the value of the synapse is I don't know 0.5, and some time elapsed, and now the synapse is 0.51, despite the fact that nothing has happened, just because of biological noise. So, in that sense, the effective resolution of a synapse will be only 0.1, because a synapse can drift between 0.5 and 0.51 in some units.
It seems to me like there could be more states, not less.
No, because if the synapse randomly flips from 0.3 to 0.31 to 0.32, then we have to take this into consideration when thinking about the model. We have to take this noise into consideration. Another way of doing it, another way of thinking about it, which turns out to be mathematically equivalent, is to say something like the following. True that this model predicts that synapses can be very strong or very weak, very positive or very negative, but there is like an upper bound that synapses cannot be stronger than something, and if you try to potentiate them beyond a particular value, you get stuck. They don't potentiate beyond a certain value. That's another way which will be mathematically equivalent to saying that synapses have a finite number of states. Yes?
But I think that, at least from what we studied about synapses in the central nervous system compared to the neural muscular junction, the whole point is that you can do fine modification, and then you lose it.
So the question is, what is a fine modification? How many such modifications are possible? What's the number of these fine modifications? Can you make 10 to the 7 modification and having the synapse maintain these, each of the 10 to the 7 different states, or maybe it's only 10 to the 5, or maybe it's only 50? This is the question. So this is the question that they asked, and I will address this question after the break. And part of it is in order to study memory, and the other reason why I'm bringing it up is because this will involve perhaps a new mathematical technique which is useful in computational neuroscience. And this we will do immediately after the break. not the mean. This term is equal to pi1.
Yeah, I want plus this.
The mean of, sorry, this would be pi1 plus something that would be normally distributed, and this mean.
Yeah, has this mean, right?
Now, if this mean is equal to minus 2, let's say that p is equal to 2. Let's say that p is equal to 2. Okay? So this, let's say that p is equal to 2. So this would be minus 2. This would be, I'm sorry, this would be 2. This would be approximately minus 1.
Yeah.
So together this would be minus 2.
Yeah.
So together with this would be either minus 3 or minus 1.
Yeah.
So the sign of minus 3 or minus 1 is always minus 1.
Yeah.
So then this cannot be
A fixed one. Yeah.
Independently of the value.
So about the one divided by two. I mean, so how is belong to one divided by two? When you say if f equal to
The reason this is true only when f is very small, because we have this approximation.
okay.
If f is close to 1/2, then this approximation will not hold. But
Okay.
basically this will be equal to 0 when f is equal to 1/2.
Okay.
Okay?
So that means in the sparse in this model, so we couldn't, if f is very small, then we couldn't found a fixed point, right?
The memory pattern will not be a fixed point. There will be other fixed points, but the memory pattern will not be. There will be another fixed point, but the memory pattern will not be a fixed point.
Okay. So that's no good, right?
No.
Okay, so that means the Hopfield model couldn't store the sparse memory.
Not this way.
No.
It needs to be modified according to the covariance rule. So this is generalization of the Hopfield model.
Okay. I will think about it. Thank you.
Okay. לוח שנה אקדמי.
נכון, לוח שנה אקדמי כתוב שאין, אבל משום מה לאלסטאק שלחו הודעה שיהיה לימודים האלה כן יהיה מיוחד.
אבל נראה שיש, מה זה?
שלישי רביעי חמישי כתוב בלוח האקדמי.
שבוע יוצא יום רביעי.
לא, שבועות רביעי, כן. שלישי רביעי פתוח חופש, אבל כתוב בלוח האקדמי וגם שלחו מייל שאין לימודים, בחלק מזה, ספציפית. להזכיר לנו שאין לימודים גם בחמישי.
יש לוח שנה אקדמי.
נכון, לוח שנה אקדמי כתוב שלישי רביעי חמישי חופש.
כן, חופש.
כתבנו בלוח שנה לא?
בלוח שנה אקדמי כתוב שלישי רביעי חופש. שלישי רביעי חמישי חופש.
אני מסתכל ממש מודפס בדלת של יונתן במשרד שלי.
לא שאל את מי הסמכות ה... לוח שנה אומר שיש לימודים.
לוח שנה של מי?
בתחילת השנה האוניברסיטה מחלקת לוחות שנה, מוכרת אותם במחיר מוזל.
יכול להיות שהתקלו את זה
לחברי
באינטרנט.
סגל. זה לאנשים. ובלוח שנה זה יש צבע לכל יום.
יש לנו לוח שנה אקדמית במזכירות שלנו. כאילו, מה זה מזכירות? האוניברסיטה העברית.
תראה. כן. חופשת שבוע. וואלה.
עוד שהתקנו אותה פה ולא בלוחות שלכם. אולי בגלל זה גם שלחו מייל במיוחד להזכיר לנו שאין, כי יכול להיות שזה נעשה שינוי תוך כדי הסמסטר.
יכול להיות. אולי בנט החליט לפרגן לסטודנטים.
סטודנטים? זה לסגל נראה לי.
לפרגן לכולם.
נכון. ווין ווין.
ווין ווין, כן. איתמר, תוכל לבדוק את הנקודה הזאת? נילי לא שם. אני צודק, בלוח השנה של ה... נשאל אותה,
כן, אני אברר.
Okay, so we are going to תודה רבה. לא הייתם צריכים. we are going to we're going to consider a different approach to the question of capacity. Other than thinking about a fixed point and stability of fixed points, we are going to make a different requirement, which is perhaps a necessary but not sufficient condition for a memory pattern. Now the idea is going to be the following. So we assume that there's a finite number of states. So we're going to assume that there's a finite number of states. For a synapse. So in the previous Hopfield model, the synapse could attain any value. So now we're going to assume that the synapse has a finite number of states. This number we will call it M. And just for simplicity, this is not a strong assumption. We will assume that synapses are bounded between 0 and 1. So the synapse can have a finite number of states between 0 and 1. Let's say, I don't know, 1 over m, 2 over m, 3 over m, 4 over m. Until, sorry?
No negative?
No negative. So the idea, this is not a strong requirement, as you will see, because we're not going to do any dynamics here. So we can, easily say that the synapses are between -half and half or something. That's not an issue. Now, whenever a memory patterns potentiate some synapses and depress some other synapses. So in the Hopfield model, you had every time that we presented the memory pattern, approximately half of the synapses were potentiated and half were depressed. Here we're making a weaker assumption that some will be potentiated and some will be depressed. Also, in the Hopfield model, let's keep it this way.
But
yes.
How do you represent, in W, potentiation, depressed synapses?
Okay, so if the synapse was 0.2 now to be 0.1.
Okay,
to become weaker.
thing.
Yes. So, and we have some rule. We have a rule for potentiation and depression, and we have a rule that tells us something about the memory pattern. So if we think about a synapse, an individual synapse over time, we expect to see something like this. So this would be the synaptic weight, and this would be as a function of time, and maybe it will look like this, where time corresponds to presentation of memory patterns. So this would be one synapse. And if we just take a different synapse, maybe the other, I just add the axes. So we said that synapses are between 0 and 1. And if we take another synapse, maybe it will look something like this. Okay? That would be another synapse. Yes?
So we moved from talking about the activity to talking only about the weight?
I'm currently talking only about the weights. Yes. Now, I cheated a little bit here in the sense that this looks like a continuous curve. But we said that synapses can attain a finite number of states. So if I will, if I will zoom into this region, I will find that in fact it looked something like this, where these are discrete values that the synapse can attain.
What's happening over time?
More and more patterns. I'm presenting a pattern to the network.
When you mean present, you mean like start an initial condition with a pattern?
No. This is in the Hopfield model. Whenever you present a pattern, there is a change in the connectivity, which will be like pi mu. You add pi mu 1 over n pi mu pj mu. And here I'm doing something, and some will potentiate, some will depress, and I have such curves for all synapses in the network.
Are you teaching the network?
I'm sorry?
Are you teaching the network?
This is the teaching of the network.
Okay.
Yes. Okay, so after a very long time, if I look at the distribution, so now I'm going to look at the distribution of synaptic efficacies in the network. So this would be the values of W. So what I'm plotting now is a distribution. So by the way, what's the distribution in the Hopfield model? What's the distribution of synaptic efficacies in the Hopfield model? Normal. Why normal? So it's approximately normal with steps that go like 1 over n. And but here we have a finite. We will have there is a finite number of different values that the synapse can attain, and there will be a distribution, a steady state distribution. So I'm plotting the steady state distribution. Maybe a simple steady state distribution would be
Are they all the same?
1, 0, 1. Well, the question whether we will get a uniform distribution like this or a different distribution will depend on the rules of the learning and something about perhaps a distribution of activities in the memory pattern. So this is one possibility. Maybe this would be one possibility, one rule, or one distribution of memories. Maybe the distribution will look something like this. I don't know. Maybe this will be the distribution. Just a second. This will depend on things that I did not tell you. I did not tell you how memories are potentiated and depressed. So, and I didn't tell you. So you cannot say anything about this distribution except for the fact that you expect that there will be a distribution.
You mean that the Jij we had is no longer the Jij for this?
Well, if you take a Hopfield model is not cannot be used here because the Hopfield model is not bounded, and so we're looking for a model which is bounded. So you can say I'm taking the Hopfield model, but whenever a synapse is larger than 1 over something, then I clip it. And then you have a distribution which perhaps will look like something like a normal distribution, a truncated normal. A different model will give you different distribution. Someone had a question here. Yes?
How do you know that the synaptic weights in the previous model is normal?
Well, because it's a sum, it's approximately normal because it's a sum of a large number of plus and minus 1 over n's. Okay, so there is a distribution. Now, let's consider a particular memory pattern, a particular point in time. So let's say that I'm now interested in considering this particular memory pattern, a memory pattern that appeared at this point in time. So what will this memory pattern do? Well, it will potentiate some of the synapses and depress other synapses. So I can define something, I will call it S, which will be equal to 1 over n. In this case, n is the number of synapses. So this is average over all synapses in the network. Now I'm considering all synapses that were potentiated at time 0. Let's call this time 0. So this would be the time where we were interested in. So I'm going to look at the sum of over all weights of all the synapses that were potentiated at this point in time. And I'm going to subtract the sum over all synapses that were depressed at this time. So the sum is over all synapses that were depressed at time 0. So I'm going to look at all the synapses that were potentiated and subtract the average over this distribution. And I'm going to subtract from this number all the synapses that were depressed and subtract the mean. So at time 0, this term will be positive, right? Because I'm taking, on average, all the values of the synapses were equal to the mean over the population before time 0. Similarly here. But here I'm separating the ones that were potentiated from the ones that were depressed. I'm subtracting the value of depressed from the value of potentiated, so I expect this number to be positive. Are you with me? So after this event at time 0, this S at time 0, we expect it to be larger than 0. Well, there will be I'm subtracting the values of the synapses that were potentiated, and I'm taking the values the values of the synapses that were potentiated, looking at this value relative to the average, and subtracting the synapses that were depressed relative to the average. So this is a positive number, this is a negative number, so the difference is a positive number. And so this is a signal of the learning. So if I take a subset of neurons, a subset of synapses, the ones that were potentiated, and look at their value and compare them to the values of the ones that were depressed, we expect this number to be positive. This is at time 0. Now, the question is, so let's say that I'm looking at the network not at time 0, but I'm looking at the network at time t, at a different value t. At a different value t, these w's will already have a different values from the values that they had at time 0 because of additional potentiation and depression. But if s of t is still larger than 0, then in principle we can think about the state of the network. Now, not the state of the activity of the network, of the neuron, but the state of the weights of all the synapses in the network. This state maintains information about the fact that at time 0, some of the synapses were potentiated, a subset of synapses were potentiated, a subset of synapses was depressed. So if this term is large, is positive and large, and we can look at time t and say, oh, it's positive and large, then we can say, okay, there was this memory pattern, or there is information about this memory pattern that was embedded in the network. Now, this is not a sufficient requirement. We don't know, even if this is positive, it's not immediately clear that we will be able to retrieve the memory pattern. But if we look at this number, and this number is not significantly different from 0, well, this implies that information about this memory pattern was lost.
What changes in the S over time? The W mean?
The W. These values will change. Because, okay, so at this point in time, this one was potentiated. So I'm bringing there's one example of potentiation. And here there's one example of depression. Okay, this happened at time 0. But from here on, there were constant changes for this one, and there were constant changes. And for this one, now at this point in time, well, the fact that this one was potentiated and this one was depressed is already lost. Now I'm not doing it for just two synapses, I'm doing it for the entire network. So initially at time 0, this number is expected to be positive by construction. But at a later time, at some point, this value is expected to change its sign, or become closer and closer to 0. And when this is insignificant, this is not significantly different from 0, then basically the information about the memory pattern was lost. You had a question.
Is it average over synapses or average over time?
Average over synapses. So this is an example of two synapses. One was potentiated, one was depressed. So I'm looking at the difference between the two. But I'm looking at this difference after more and more memory patterns were embedded in a way that I did not say exactly how. Yes?
So in this case, you really get an S greater than 0, right? Because
yes.
The upper one was
potentiated.
But if you have the different case when this one is depressed and the other one, then you get this.
Well, you have to remember that these are just two synapses out of n squared synapses. So on average, if I randomly choose synapses for potentiation and depression, I randomly choose synapses for potentiation and depression. Yes, I randomly choose synapses for potentiation and depression.
I mean, why is it necessarily negative? I mean, the W payment. You say it's negative. Is it negative over time or only at time 0?
At time 0.
But why? I mean.
By construction, I took a subset of synapses, a randomly chosen subset of synapses, and I depressed them. So the sum over all these synapses, on average, is less. Well, on average, these synapses have a value that is smaller than average.
But this is just an initial condition.
Initial condition, but yes, and as long as this is positive, then it means that there is a trace in the network, in the connectivity about the memory pattern. There's a trace. If it's no longer positive, then it means that this trace is lost. Yes?
So this is not a specific memory pattern, or maybe?
Well, I'm interested in the way that I'm doing it is I'm putting more and more memory patterns, and I'm randomly choosing one point and seeing how long will I still be able to memorize, to maintain memory from this point onwards. Yes.
Maybe it's the same question.
Yes.
But isn't it possible that half were depressed and half were
Yes.
potentiated, but then it would still be 0?
No, because I'm choosing the ones that were potentiated minus the ones that were depressed. It's not an this is not a this sum is on specifically on those that were potentiated minus those that were depressed.
It might be that this difference is 0, but the information.
Well, we don't expect this to be 0 because these were potentiated, so these have on average higher weight than those that were depressed. Average over all those times.
Technically, value after they were depressed or potentiated.
Yes. Yes.
So just to make sure, the average W is a function of the distribution and it's a constant.
The average, you mean?
What you subtract.
Well, at a steady state, will be an average. Yes, an average over the distribution.
Okay, and you're going to tell us what else changes the type memory?
No, there's nothing. Only memories. Only memories change the values of these synapses.
So if this will always be positive, so how can you get it?
No, I'm not saying that I did not prove that it will always be positive. I just said that at time 0 it will be positive. Later on, it could change.
Prove it that time 0 is positive?
Well, kind of, right? Because the distribution of these weights is the same as the distribution of all weights in the network. So before potentiation, they had the same weight. I potentiated some, so this becomes positive. I depressed some, so this is negative. A positive minus a negative number is positive.
So how in different times can be negative?
Well, because, you see here, because other memory patterns could result in more potentiation, more depression of the others.
Yeah, but mean of W is constant So each time you...
The mean of W is constant. I mean, we are in a steady state after. This is like an ongoing process. Constantly we add memories to the system. So
Not a function of time, the average?
this average, no, it's an average. It's a stationary distribution basically, because where we potentiated some and depressed some.
And can you repeat why the change of the sign of F would maybe reflect God?
Well, this would imply that even if you would go now at all synapses in the network and look who was potentiated and who was depressed, and you find that the ones that were potentiated are not stronger than the ones that were depressed at this point in time, then there's nothing else left. It's a necessary but not sufficient condition. It implies, I mean, let's say that you ask a question, I want to know whether these synapses were potentiated and these this population was potentiated and this population was depressed. A particular memory pattern that even you know what it is. So you know what it was supposed to do to the network. Now you go, you search all synapses and you see what happened to them, and you just don't know whether these were potentiated or not. Then there's nothing else, nothing left.
But what is the quality of this trait?
So I'm saying it's a necessary but not sufficient condition. Okay, so one way of yes.
So the mean of the W is fixed number for all time? Or
Yes, it's a fixed number for all time.
Or for each time?
No, it's a fixed. Where it's a steady state, it's a fixed number. It will be clear. It becomes clear later. Allow me to continue. So, one way of thinking about it is to look at the way what happened to the distribution of occupancies to those synapses that were potentiated, and compare it to the distribution of occupancies for those synapses that were depressed. So basically, let's consider this particular example. So for those that were, if I just look at the distribution of occupancies, of values of weights for those that were potentiated, just for the population that was potentiated, maybe we will find that it looks something like this. So there will be a larger number of weights that are stronger, and a smaller number of weights that are weaker. And perhaps this would look more or less the same, and then perhaps it will grow. So the potentiation will take a subgroup of synapses in the network and will change the distribution of values that it can attain. These are for the particular synapses that were potentiated at time t is equal to 0. And similarly, we'll have something for the ones that were depressed. So for ones that were depressed, there will be a larger number, a larger fraction that will have small values, and a smaller value that will have a large value. So this would be depressed at t being equal to 0. So the fact that this value is positive results from the fact that the relative occupancy of the different states of the synapse changed for those that were potentiated and depressed. Now, what we will be interested in is how these two distributions, the distribution for those that were potentiated and the distribution for those that were depressed, will change over time. So if these two distributions will become identical to the steady state distribution, then this implies that this value will be equal to 0. If after a long time the two distributions are still different, this implies that this value is still positive, which implies that we can still extract information, or that there is information in the network about this particular memory pattern that was embedded at time t being equal to 0. Is it clear?
If it's not,
I'm sorry?
if it's not identical?
Well, if this one, even after a long time, the occupancy of this population is still more positive, and the other one, the occupancy, is still more negative, more to the stronger, the other one is more to the weaker, then there's still information in the network about the embedding of this memory pattern. This is the idea. So just a second. So basically what we need to do now is consider the dynamics of the distribution of occupancies for the population that was potentiated and the dynamics over time of the occupancy or the distribution of weight for those that were depressed. Yes, you had a question.
Yeah, this only looks on the number of synapses that were potentiated or depressed, right?
No, the weight. This is the weight. What you have here is the distribution of weights. So now the blue would be the distribution of weight for the subpopulation that was potentiated at time t is equal to 0, and the orange would be the distribution of weight for the subpopulation that was depressed at time t being equal to 0.
Like the memory is not what it does to single synapses. Like the identity of each synapse doesn't matter.
The way that we think about this would be like a bound. If we show that the two distributions at some point in time converge to exactly the same value, then it means that there's no information in the population, and there will be also no information at a single synapse level. If we find a difference, now we can start arguing about whether this is sufficient to extract the memory pattern. So our goal would be to understand how this distribution of weights changes over time, given different rules of synaptic plasticity. This is what we are going to do. Now, in order to do that, we will forget about synapses, we will forget about Hopfield, we'll forget about memory, and make a detour that will start today. And I was hoping that it will end today, but it will not end today. It will end on Sunday. And this detour is a detour about Markov chains, first order Markov chains. So now we forget about this. This is our motivation. We will go back to it on Sunday, and we talk about first order Markov chains. Unless all of you have already...
No.
Okay. This was a definite answer and a very clear one. Okay, so the topic of the next 5 minutes, 10 minutes, is Markov chains. We will only talk about first order. And the relevance to this problem will become clear on Sunday. So now we're going to consider a problem, a different problem. And so the way to think about it is some kind of the example that I will be using is a random walk in a house. I know that you're all very excited. So we're considering a house. This is a house. Okay, that's my house. And we have 4 rooms in the house. Let's draw the rooms. So in my house, all rooms have letters in them. I don't know if it's normal, but that's how my house looks like. Okay, this is how my house looks like. And so you see there are 4 rooms in my house. And Friday nights I get drunk and start walking in my house. Now, as a result of being drunk, I randomly go from one room to the other. And the way that I do it in steps. So we're considering time steps. Every time step I move from one room to the other. I don't know, I'm looking for something perhaps. But I'm doing it randomly, such that the probability of using a door of using all doors are equal. So if I'm in a time t, I'm in room D, then at time t plus 1, I will necessarily be in room C. But because there's only one room, only one door from D to C. Okay? But if I'm currently in room C, then the probability that I will move to room A, room B, or room D is 1 over 3. If I'm at A, I will either move to B or C with the probability 1/2, and so on. Yes? I must. Yes. 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 So we can. So I'm going to quantify this. So the probability of moving from A to A, that's your question, is 0. The probability of moving to B from A is 1/2. The probability of moving to C from A is 1/2. The probability of moving to D from A is 0. And now we can talk about the probability of moving from B to A, which will be equal to 1/2, and there will be probability of moving from C to A, which will be equal to 1 over 3, and so on. So this will be quantifying my house. Another way of doing it is using this. I don't know the name. If anyone knows the name of this notation, well, it's like it's Markov Chains, I guess. So the probability of transition from A to C is 1/2. Probability of moving from A to B is 1/2. Probability of moving from C to A is 1 over 3. From C to B, 1 over 3. From C to D is 1 over 3. And from D to C is 1. And I have from B to C, B to A and A. Well, B to A is 1/2. And I guess I forgot something, but I think you got the point. Now, one question that you may ask yourself, I don't know if you will ask yourself, but you may ask yourself, is where am I going to be after some time steps, given that I was somewhere at some point in time? I don't know if it's a very interesting question, but still you may ask yourself. So for example, what's the probability, let's do it here. What's the probability that I will be in state A at time t being equal to 1? Well, okay, so I need to know where I was in the previous time step. So this would be equal to the probability that I was in A at time 0 times probability of transition from A to A, plus the probability that I was in state B at time t equal to 0 times the probability of transition from B to A, and so on. Right? That's is it clear? I just have to write four such equations, and we can use a matrix notation. We can use a matrix notation and say that the probability to be in state A, B, C, and D at time t being equal to 1 is equal to some kind of a transition matrix times the probability that I was in state A, B, C, and D at time t being equal to 0. So what is this matrix? Well, this is a matrix of all these transitions. So the first term in the matrix will be A to A, right? Probability of being at A time t equal to 1 is equal to the probability of being at time t equal to 0 in point A times the probability of transition from A to A. And here I will have B to A, C to A, and D to A. And now we will have A to B, and so on. So this is writing these equations in matrix notation, and I will call this matrix M for no good reason, and M in our case will be equal to 0, 1/2, 1/3, 0, 1/2, 0, 1/3, 0, 1/2, 1/2, 0, 1, 0, 0, 1/3, 0, if I'm not mistaken. Which I probably am, but you're too tired to notice anyway, so why should I care? Okay. So this is a rather useful matrix. It is useful because so let's call this probability of A, B, C, D, I'll just call it P. So P at time t being equal to 1 is equal to the matrix M times P at time t equal to 0. This is what's written here. Now where am I going to be after 2 time steps? This would be just M squared times P times t0 and so on. So if I want to know where I'm going to be on Saturday morning after n time steps, all I need to do is to take this matrix and compute this matrix to the power of n. And if you know the initial conditions, then we're done. Right? Yes?
In intuition, after a lot of time, p in time 0, it's not zero.
So what you tell me is that after a long time you don't care about my initial location.
Yes, depends on M.
It depends on M.
Yeah. If your initial condition, you can get out of it. Yeah.
Okay, we will see. I don't know what's long time. I know Saturday morning is a long time, but it depends on M, depends on N. But we will see. That's exactly the point. I mean, going back to our original problem, forget about me walking lonely and drunk in my house between Friday and Saturday. Think about the synapse. Not my synapse. The synapse in the model. Now the synapse changes its state in response to memory patterns that appear randomly and have some that are drawn from some distribution. Now, if after a very long time the value of the synapse is independent of the initial value, this would be the potentiation and depression at time t0, this would imply that the memory is lost. It's a necessary condition, not sufficient, a necessary condition that the memory is already lost. So by doing this trick for the synapse, learning when the synapse, this initial condition is no longer important, we will be able to obtain a measure, handle to the memory capacity of the network, independently of the particular readout that we were considering previously, which was a fixed point of some dynamics. אין סליחה ואין מחילה. Okay, that's a very good point to stop, and we will continue on Sunday.